Atmospheric particulate matter also known as particulates or particulate matter are particles of solid or liquid matter suspended in the Earth's atmosphere as atmospheric aerosol, a term which refers to the particulate air mixture, as opposed to the particulate matter alone. However, it is common to use the term aerosol to refer to the particulate component alone. Sources of particulate matter can be man-made or natural. They can adversely affect human health and also have impacts on climate and precipitation. Subtypes of atmospheric particle matter include suspended particulate matter, respirable suspended particle, fine particles, ultrafine particles, and soot. The IARC and WHO designates airborne particulates a Group 1 carcinogen. Particulates are the deadliest form of air pollution due to its ability to penetrate deep into the lungs and bloodstreams unfiltered, causing permanent DNA mutations, heart attacks and premature death. In 2013, a Danish study involving 312,944 people in 9 European countries revealed that there was no safe level of particulates and that for every increase of 10 I1/4 gram per meter 3 in PM10, the lung cancer rate rose 22%. The smaller PM2.5 were particularly deadly, with a 36% increase in lung cancer per 10 I1/4 gram per meter 3 as it can penetrate deeper into the lungs. Sources of atmospheric particulate matter. Some particulates occur naturally, originating from volcanoes, dust storms, forest and grassland fires, living vegetation, and sea spray. Human activities, such as the burning of fossil fuels in vehicles, power plants and various industrial processes also generate significant amounts of particulates. Coal combustion in developing countries is the primary method for heating homes and supplying energy. Because salt spray over the oceans is the overwhelmingly most common form of particulate in the atmosphere, anthropogenic aerosols those made by human activity currently account for about 10% of the total mass of aerosols in our atmosphere. Composition. The composition of aerosols and particles depends on their source. Wind-blown mineral dust tends to be made of mineral oxides and other material blown from the Earth's crust. This particulate is light-absorbing. Sea salt is considered the second largest contributor in the global aerosol budget, and consists mainly of sodium chloride originated from sea spray. Other constituents of atmospheric sea salt reflect the composition of seawater, and thus include magnesium, sulfate, calcium, potassium, etc. In addition, sea spray aerosols may contain organic compounds, which influence their chemistry. Secondary particles derive from the oxidation of primary gases such as sulfur and nitrogen oxides into sulfuric acid and nitric acid. The precursors for these aerosols that is the gases from which they originate may have an anthropogenic origin and a natural biogenic origin. In the presence of ammonia, secondary aerosols often take the form of ammonium salts. That is ammonium sulfate and ammonium nitrate. In the absence of ammonia, secondary compounds take an acidic form as sulfuric acid and nitric acid, all of which may contribute to the health effects of particulates. Secondary sulfate and nitrate aerosols are strong light scatterers. This is mainly because the presence of sulfate and nitrate causes the aerosols to increase to a size that scatters light effectively. Organic matter can be either primary or secondary, the latter part deriving from the oxidation of VOCs. Organic material in the atmosphere may either be biogenic or anthropogenic. Organic matter influences the atmospheric radiation field by both scattering and absorption. Another important aerosol type is elemental carbon. This aerosol type includes strongly light-absorbing material and is thought to yield large positive radiative forcing. Organic matter and elemental carbon together constitute the carbonaceous fraction of aerosols. Secondary organic aerosols, tiny tar balls resulting from combustion products of internal combustion engines, have been identified as a danger to health. The chemical composition of the aerosol directly affects how it interacts with solar radiation. The chemical constituents within the aerosol change the overall refractive index. The refractive index will determine how much light is scattered and absorbed. The composition of particulate matter that generally causes visual effects such as smog consists of sulfur dioxide, nitrogen oxides, carbon monoxide, mineral dust, organic matter, and elemental carbon, also known as black carbon or soot. The particles are hygroscopic due to the presence of sulfur, and SO2 is converted to sulfate when high humidity and low temperatures are present. This causes the reduced visibility and yellow color. Size distribution of particulates. Aerosol particles of natural origin tend to have a larger radius than human-produced aerosols such as particle pollution. The false color maps in the third image on this page show where there are natural aerosols, human pollution, or a mixture of both, monthly. Among the most obvious patterns that the size distribution time series shows is that in the Planeta Euro unregistered trademark S most southerly latitudes, nearly all the aerosols are large, but in the high northern latitudes, smaller aerosols are very abundant. Most of the southern hemisphere is covered by ocean, where the largest source of aerosols is natural sea salt from dried sea spray. Because land is concentrated in the northern hemisphere, the amount of small aerosols from fires and human activities is greater there than in the southern hemisphere. Over land, patches of large radius aerosols appear over deserts and arid regions, most prominently, the Sahara Desert in North Africa and the Arabian Peninsula, where dust storms are common. Places where human-triggered or natural fire activity is common are dominated by smaller aerosols. Human-produced pollution is largely responsible for the areas of small aerosols over developed areas such as the eastern United States and Europe, especially in the summer. Satellite measurements of aerosols, called aerosol optical thickness, are based on the fact that the particles change the way the atmosphere reflects and absorbs visible and infrared light. As shown in the seventh image on this page, an optical thickness of less than 0.1 indicates a crystal clear sky with maximum visibility, whereas a value of 1 indicates very hazy conditions. Deposition processes. In general, the smaller and lighter a particle is, the longer it will stay in the air. Larger particles tend to settle to the ground by gravity in a matter of hours, whereas the smallest particles can stay in the atmosphere for weeks and are mostly removed by precipitation. Diesel particulate matter is highest near the source of emission. Any info regarding DPM and the atmosphere, flora, height, and distance from major sources would be useful to determine health effects. Control technologies. Particulate matter emissions are highly regulated in most industrialized countries. Due to environmental concerns, most industries are required to operate some kind of dust collection system to control particulate emissions. These systems include inertial collectors, fabric filter collectors, wet scrubbers, and electrostatic precipitators. Cyclonic separators are useful for removing large, coarse particles and are often employed as a first step or pre-cleaner to other more efficient collectors. Well-designed cyclonic separators can be very efficient in removing even fine particulates, and may be operated continuously without requiring frequent shutdowns for maintenance. Fabric filters or baghouses are the most commonly employed in general industry. They work by forcing dust-laden air through a bag-shaped fabric filter, leaving the particulate to collect on the outer surface of the bag and allowing the now clean air to pass through to either be exhausted into the atmosphere or in some cases recirculated into the facility. Common fabrics include polyester and fiberglass, and common fabric coatings include PTFE. The excess dust buildup is then cleaned from the bags and removed from the collector. Wet scrubbers pass the dirty air through a scrubbing solution, allowing the particulate to attach to the liquid molecules. Electrostatic precipitators electrically charge the dirty air as it passes through. The now charged air then passes by large electromagnetic plates which attract the charged particle in the airstream, collecting them and leaving the now clean air to be exhausted or recirculated. Climate effects. Atmospheric aerosols affect the climate of the Earth by changing the amount of incoming solar radiation and outgoing terrestrial long-wave radiation retained in the Earth system. This occurs through several distinct mechanisms which are split into direct, indirect and semi-direct aerosol effects. The aerosol climate effects are the biggest source of uncertainty in future climate predictions. The Intergovernmental Panel on Climate Change, Third Assessment Report, says, while the radiative forcing due to greenhouse gases may be determined to a reasonably high degree of accuracy, the uncertainties relating to aerosol radiative forcings remain large, and rely to a large extent on the estimates from global modeling studies that are difficult to verify at the present time. Aerosol radiative effects. Direct effect. The direct aerosol effect consists of any direct interaction of radiation with atmospheric aerosol, such as absorption or scattering. It affects both short and long-wave radiation to produce a net negative radiative forcing. The magnitude of the resultant radiative forcing due to the direct effect of an aerosol is dependent on the albedo of the underlying surface, as this affects the net amount of radiation absorbed or scattered to space. For example, if a highly scattering aerosol is above a surface of low albedo, it has a greater radiative forcing than if it was above a surface of high albedo. The converse is true of absorbing aerosol, with the greatest radiative forcing arising from a highly absorbing aerosol over a surface of high albedo. The direct aerosol effect is a first-order effect and is therefore classified as a radiative forcing by the IPCC. The interaction of an aerosol with radiation is quantified by the single scattering albedo, the ratio of scattering alone to scattering plus absorption of radiation by a particle. The SSA tends to unity if scattering dominates, with relatively little absorption, and decreases as absorption increases, becoming zero for infinite absorption. For example, sea salt aerosol has an SSA of 1, as a sea salt particle only scatters, whereas soot has an SSA of 0.23, showing that it is a major atmospheric aerosol absorber. Indirect effect. The indirect aerosol effect consists of any change to the Earth's radiative budget due to the modification of clouds by atmospheric aerosols, and consists of several distinct effects. Cloud droplets form onto pre-existing aerosol particles, known as cloud condensation nuclei. For any given meteorological conditions, an increase in CCN leads to an increase in the number of cloud droplets. This leads to more scattering of short-wave radiation, that is an increase in the albedo of the cloud, known as the cloud albedo effect, first indirect effect or TWIMI effect. Evidence supporting the cloud albedo effect has been observed from the effects of ship exhaust plumes and biomass burning on cloud albedo compared to ambient clouds. The cloud albedo aerosol effect is a first-order effect and therefore classified as a radiative forcing by the IPCC. An increase in cloud droplet number due to the introduction of aerosol acts to reduce the cloud droplet size, as the same amount of water is divided between more droplets. This has the effect of suppressing precipitation, increasing the cloud lifetime, known as the cloud lifetime aerosol effect, second indirect effect or Albrecht effect. This has been observed as the suppression of drizzle in ship exhaust plume compared to ambient clouds, and inhibited precipitation and biomass burning plumes. This cloud lifetime effect is classified as a climate feedback by the IPCC due to the interdependence between it and the hydrological cycle. However, it has previously been classified as a negative radiative forcing. Semi-direct effect. The semi-direct effect concerns any radiative effect caused by absorbing atmospheric aerosol such as soot, apart from direct scattering and absorption, which is classified as the direct effect. It encompasses many individual mechanisms, and in general is more poorly defined and understood than the direct and indirect aerosol effects. For instance, if absorbing aerosols are present in a layer aloft in the atmosphere, they can heat surrounding air, which inhibits the condensation of water vapor, resulting in less cloud formation. Additionally, heating a layer of the atmosphere relative to the surface results in a more stable atmosphere due to the inhibition of atmospheric convection. This inhibits the convective uplift of moisture, which in turn reduces cloud formation. The heating of the atmosphere aloft also leads to a cooling of the surface, resulting in less evaporation of surface water. The effects described here all lead to a reduction in cloud cover, that is an increase in planetary albedo. The semi-direct effect classified as a climate feedback, by the IPCC due to the interdependence between it and the hydrological cycle. However, it has previously been classified as a negative radiative forcing. Roles of different aerosol species. Sulfate aerosol. Sulfate aerosol has two main effects, direct and indirect. The direct effect, via albedo, is a cooling effect that slows the overall rate of global warming. The IPCC's best estimate of the radiative forcing is -0.4 watts per square meter with a range of -0.2 to -0.8 with MAR squared, but there are substantial uncertainties. The effect varies strongly geographically, with most cooling believed to be at and downwind of major industrial centers. Modern climate models addressing the attribution of recent climate change take into account sulfate forcing, which appears to account for the slight drop in global temperature in the middle of the 20th century. The indirect effect is more uncertain but is believed to be a cooling. Black carbon, or carbon black, or elemental carbon, often called soot, is composed of pure carbon clusters, skeleton balls and buckyballs, and is one of the most important absorbing aerosol species in the atmosphere. It should be distinguished from organic carbon, clustered or aggregated organic molecules on their own or permeating an EC buckyball. BC from fossil fuels is estimated by the IPCC in the fourth assessment report of the IPCC, 4AR, to contribute a global mean radiative forcing of +0.2 with MAR squared, with a range +0.1 to +0.4 with MAR squared. Bond al., however, states that the best estimate for the industrial era direct radiative forcing of atmospheric black carbon is +0.71 with MAR squared with 90% uncertainty bounds of with MAR squared with total direct forcing by all black carbon sources, without subtracting the pre-industrial background, is estimated as +0.88 with MAR squared. Instances of aerosol affecting climate. Volcanoes are a large natural source of aerosol and have been linked to changes in the Earth's climate, often with consequences for the human population. Eruptions linked to changes in climate include the 1600 eruption of Hainapidana, which was linked to the Russian famine of 1601 to 1603, leading to the deaths of 2 million, and the 1991 eruption of Mount Pinatubo, which caused a global cooling of approximately 0.5 AA degrees Celsius lasting several years. Research tracking the effect of light scattering aerosols in the stratosphere during 2010 and comparing its pattern to volcanic activity show a close correlation. Simulations of the effect of anthropogenic particles showed little influence at present levels. Aerosols are also thought to affect weather and climate on a regional scale. The failure of the Indian monsoon has been linked to the suppression of evaporation of water from the Indian Ocean due to the semi-direct effect of anthropogenic aerosol. Recent studies of the Sahel drought and major increases since 1967 in rainfall over the Northern Territory, Kimberley, Pilbara and around the Nullarbor Plain have led some scientists to conclude that the aerosol haze over South and East Asia has been steadily shifting tropical rainfall in both hemispheres southward. The latest studies of severe rainfall declines over southern Australia since 1997 have led climatologists there to consider the possibility that these Asian aerosols have shifted not only tropical but also mid-latitude systems southward. Health effects. Increased levels of fine particles in the air as a result of anthropogenic particulate air pollution is consistently and independently related to the most serious effects, including lung cancer and other cardiopulmonary mortality. The large number of deaths and other health problems associated with particulate pollution was first demonstrated in the early 1970s and has been reproduced many times since. PM pollution is estimated to cause 22,000 to 52,000 deaths per year in the United States and contributed to 370,000 premature deaths in Europe during 2005. The effects of inhaling particulate matter that have been widely studied in humans and animals now include asthma, lung cancer, cardiovascular issues, respiratory diseases, birth defects, and premature death. The size of the particle is a main determinant of where in the respiratory tract the particle will come to rest when inhaled. Because of their small size, particles on the order of 10 micrometers or less can penetrate the deepest part of the lungs such as the bronchioles or alveoli. Larger particles are generally filtered in the nose and throat via cilia and mucus, but particulate matter smaller than about 10 micrometers, referred to as PM10, can settle in the bronchi and lungs and cause health problems. The 10 micrometer size does not represent a strict boundary between respirable and non-respirable particles, but has been agreed upon for monitoring of airborne particulate matter by most regulatory agencies. Similarly, particles smaller than 2.5 micrometers, PM2.5, tend to penetrate into the gas exchange regions of the lung, and very small particles may pass through the lungs to affect other organs. Penetration of particles is not wholly dependent on their size. Shape and chemical composition also play a part. To avoid this complication, simple nomenclature is used to indicate the different degrees of relative penetration of a PM particle into the cardiovascular system. Inhalable particles penetrate no further than the bronchi as they are filtered out by the cilia. Thoracic particles can penetrate right into terminal bronchioles, whereas PM which can penetrate to alveoli and hence the circulatory system are termed respirable particles. A study published in the Journal of the American Medical Association indicates that PM2.5 leads to high plaque deposits in arteries, causing vascular inflammation and atherosclerosis, a hardening of the arteries that reduces elasticity, which can lead to heart attacks and other cardiovascular problems. In addition, a new study published January 21, 2014 in the British Medical Journal reported that long-term exposure to ambient air pollution is linked with incidence of coronary events. The study design was prospective cohort studies and meta-analysis of the results, and it was done in 11 cohorts participating in the European Study of Cohorts for Air Pollution Effects. 100,166 participants were enrolled and were followed for an average of 11.5 years. According to the study result, an increase in estimated annual exposure to PM2.5 of just 5 AA microgram M3 was linked with a 13% increased risk of heart attacks. The World Health Organization estimates that fine particulate air pollution causes about 3% of mortality from cardiopulmonary disease, about 5% of mortality from cancer of the trachea, bronchus, and lung, and about 1% of mortality from acute respiratory infections in children under 5 years, worldwide. doi, 10.1080/1528739059093616 PMID 16024504. Researchers suggest that even short-term exposure at elevated concentrations could significantly contribute to heart disease. A study in The Lancet concluded that traffic exhaust is the single most serious preventable cause of heart attack in the general public, the cause of 7.4% of all attacks. The smallest particles, less than 100 nanometers, may be even more damaging to the cardiovascular system. There is evidence that particles smaller than 100 nanometers can pass through cell membranes and migrate into other organs, including the brain. It has been suggested that particulate matter can cause similar brain damages that found in Alzheimer patients. Particles emitted from modern diesel engines are typically in the size range of 100 nanometers. In addition, these soot particles also carry carcinogenic components like benzopyrenes adsorbed on their surface. It is becoming increasingly clear that the legislative limits for engines, which are in terms of emitted mass, are not a proper measure of the health hazard. One particle of 10 AA micrometer diameter has approximately the same mass as 1 million particles of 100 nm diameter, but it is clearly much less hazardous, as it probably never enters the human body and if it does, it is quickly removed. Proposals for new regulations exist in some countries, with suggestions to limit the particle's surface area or the particle count. A further complexity that is not entirely documented is how the shape of PM can affect health. Of course, the dangerous needle-like shape of asbestos is widely recognized to lodge itself in the lungs with often dire consequences. Geometrically angular shapes have more surface area than rounder shapes, which in turn affects the binding capacity of the particle to other, possibly more dangerous substances. The inhalable dust fraction is the fraction of dust that enters the nose and mouth and may be deposited anywhere in the respiratory tract. The thoracic fraction is the fraction that enters the thorax and is deposited within the lung airways and the gas exchange regions. The respiratory fraction is what is deposited in the gas exchange regions. The site and extent of absorption of inhaled gases and vapors are determined by their solubility in water. Absorption is also dependent upon airflow rates and the partial pressure of the gases in the inspired air. The fate of a specific contaminant is dependent upon the form in which it exists. Inhalation also depends upon the breathing rate of the subject. Researchers at the Johns Hopkins Bloomberg School of Public Health have conducted the largest nationwide study on the acute health effects of coarse particle pollution. Coarse particles are airborne pollutants that fall between 2.5 and 10 micrometers in diameter. The study, published in the May 14, 2008, edition of JAMA, found evidence of an association with hospital admissions for cardiovascular diseases but no evidence of an association with the number of hospital admissions for respiratory diseases. After taking into account fine particle levels, the association with coarse particles remained but was no longer statistically significant. Particulate matter studies in Bangkok, Thailand indicated a 1.9% increased risk of dying from cardiovascular disease, and 1.0% risk of all disease for every 10 micrograms per cubic meter. Levels averaged 65 in 1996, 68 in 2002, and 52 in 2004. Decreasing levels may be attributed to conversions of diesel to natural gas combustion as well as improved regulations. The Mongolian government agency has recorded a 45% increase in the rate of respiratory illness in the past 5 years. Bronchial asthma, chronic obstructive pulmonary disease and interstitial pneumonia are the most common ailments treated by area hospitals. Levels of premature death, chronic bronchitis, and cardiovascular disease are increasing at a rapid rate. Effects on vegetation. Particulate matter can clog stomatal openings of plants and interfere with photosynthesis functions. In this manner, high particulate matter concentrations in the atmosphere can lead to growth stunting or mortality in some plant species. Regulation. Due to the highly toxic health effects of particulate matter, most governments have created regulations both for the emissions allowed from certain types of pollution sources and for the ambient concentration of particulates. The IARC and WHO designates particulates a Group 1 carcinogen. Particulates are the deadliest form of air pollution due to its ability to penetrate deep into the lungs and bloodstreams unfiltered, causing permanent DNA mutations, heart attacks and premature death. In 2013, a Danish study involving 312,944 people in 9 European countries revealed that there was no safe level of particulates in net for every increase of 10 I1/4 gram per meter 3 in PM10. The lung cancer rate rose 22%. The smaller PM2.5 were particularly deadly, with a 36% increase in lung cancer per 10 I1/4 gram per meter 3 as it can penetrate deeper into the lungs. Australia has set limits for particulates in the air. In Canada the standard for particulate matter is set nationally by the Federal Provincial Canadian Council of Ministers of the Environment. Jurisdictions may set more stringent standards. The CCME standard for particulate matter 2.5 is 30 AI1/4 gram per meter 3. China has set limits for particulates in the air. European Union. The European Union has established the European emission standards which include limits for particulates in the air, to the first target value entered into force January 1, 2010. Limit value enters into force January 1, 2015. Hong Kong has set limits for particulates in the air. Japan has set limits for particulates in the air. South Korea has set limits for particulates in the air. The United States Environmental Protection Agency has set standards for PM10 and PM2.5 concentrations. California. In October 2008, the Department of Toxic Substances Control, within the California Environmental Protection Agency, announced its intent to request information regarding analytical test methods, fate and transport in the environment, and other relevant information from manufacturers of carbon nanotubes. DTSC is exercising its authority under the California Health and Safety Code, Chapter 699, Sections 57,018 to 57,020. These sections were added as a result of the adoption of Assembly Bill AB 289. They are intended to make information on the fate and transport, detection and analysis, and other information on chemicals more available. The law places the responsibility to provide this information to the department on those who manufacture or import the chemicals. On January 22, 2009, a formal information request letter was sent to manufacturers who produce or import carbon nanotubes in California, or who may export carbon nanotubes into the state. This letter constitutes the first formal implementation of the authorities placed into statute by AB 289 and is directed to manufacturers of carbon nanotubes, both industry and academia within the state, and to manufacturers outside California who export carbon nanotubes to California. This request for information must be met by the manufacturers within 1 year. DTSC is waiting for the upcoming January 22, 2010 deadline for responses to the data call-in. The California Nano Industry Network and DTSC hosted a full-day symposium on November 16, 2009 in Sacramento, CA. This symposium provided an opportunity to hear from nanotechnology industry experts and discuss future regulatory considerations in California. DTSC is expanding the specific chemical information call-in to members of the nanometal oxides. The latest information can be found on their website. Colorado. Key points in the Colorado plan include reducing emission levels and solutions by sector. Agriculture, transportation, green electricity, and renewable energy research are the main concepts and goals in this plan. Political programs such as mandatory vehicle emissions testing and the prohibition of smoking indoors are actions taken by local government to create public awareness and participation in cleaner air. The location of Denver next to the Rocky Mountains and wide expanse of plains makes the metro area of Colorado's capital city a likely place for smog and visible air pollution. Affected areas. The most concentrated particulate matter pollution tends to be in densely populated metropolitan areas in developing countries. The primary cause is the burning of fossil fuels by transportation and industrial sources. Ulaanbaatar, Mongolia's capital city Ulaanbaatar, is affected by choking air pollution caused by coal and wood burning. The new market economy of the country and its very cold winter seasons have led to the formation of shanty towns, where 60% of the population of this, the coldest capital city in the world, reside. The poor in these districts cook and heat their wood houses with indoor stoves fueled by wood or coal. The resulting air pollution is characterized by raised sulfur dioxide and nitrogen oxide levels and very high concentrations of airborne particles and particulate matter. Measurements carried out in Ulaanbaatar show that among the air pollution components, this dense PM has by far the most deadly health consequences. During the winter months in particular, urban air obscures vision, and negatively impacts human health. The air pollution also affects the visibility in the city to such an extent that airplanes on some occasions are prevented from landing at the local airport. The annual average temperature in Ulaanbaatar is 0.8 degrees Celsius, making it the world's coldest capital city. About 40% of the population in Ulaanbaatar, Mongolia lives in apartments, about 80% of them supplied with central heating systems from 3 combined heat and power plants. The power plants consumed almost 3.4 million tons of coal in 2007. The pollution control technology is in poor condition. In addition to stack emissions, another unaccounted for source in the emission inventory is the fly ash from the ponds where fly ash is disposed. Removed fly ash is sent to settling tanks where the sedimented dust is collected and sent to the ash pond. These ash ponds are continually subjected to wind erosion in the dry season. In Ulaanbaatar, Mongolia, annual seasonal average particulate matter concentrations have been recorded as high as 279 AA microgram M3. To put this in perspective, the World Health Organization's recommended PM10 level is 20 AA microgram M3. This means that Ulaanbaatar's PM10 levels are 14 times higher than what is recommended. This also means that Ulaanbaatar has left northern China's most polluted cities in its wake. Compared to such high concentrations, Some cities in northern China and South Asia also had concentrations above 200 AA microgram M3 up to a few years ago. The PM levels in Chinese cities are still extreme in recent years, reaching an all-time high in Beijing on January 12, 2013, of 993 AA microgram M3. To monitor the air quality of South China, the U.S. consul at Guangzhou set a PM2.5 monitor on Shamian Island in Guangzhou, Guangdong Province and show data on the official website, social platforms like Twitter and Facebook and the consular application GZAIR. See also, references. Further reading, article at artobservatory.nasa.gov describing the possible influence of aerosols on the climate, the Intergovernmental Panel on Climate Change chapter on atmospheric aerosols and their radiative effects, inside EPA.com. Study links air toxics to heart disease in mice amid EPA controversy, Preening, Othmar and E. James Davis, History of Aerosol Science, Österreichische Akademie der Wissenschaften, ISBN 3-7001-2915-7, Gianvranis Zial, Particulate Matter from Tobacco vs. Diesel Car Exhaust, An Educational Perspective. Tobacco Control 13. S219-221, Jeff Charlton Pandemic Planning, A Review of Respirator and Mask Protection Levels. Hines, William C., Aerosol Technology, Properties, Behavior, and Measurement of Airborne Particles, Wiley Interscience, ISBN 0-471-19410-7, External links, U.S. Environmental Protection Agency Resources page, Particulate Matter, National Pollutant Inventory Particulate Matter Fact Sheet, CDC, NIOSH Pocket Guide to Chemical Hazards, WHO Europe Reports, Health Aspects of Air Pollution and Answer to Follow-up Questions from CAFE, American Association for Aerosol Research, Particulate Air Pollution, Aerosol Society The Development of Aerosol Science in the United Kingdom, Watch and Read Dirty Little Secrets, 2006. Australian Science documentary on health effects of fine particle pollution from vehicle exhausts, Aerosol Science and Technology, Canada-wide standards, Little Green Data Book 2007, World Bank. List CO2 and PM statistics by country. Air pollution in world cities, European Environment Agency, Airborne Particles and Their Health Effects A multinational research network, measurement of personal exposure to PM10 in the non-workplace environment using passive sampling techniques by J. Aitken, L. C. Kenny and A. Sauter. IOM Research Report TM05, High Aspect Respirable Particles by Dr. C. Poland, Integrated Science Assessment for Particulate Matter 48 MB, Integrated Science Assessment for Particulate Matter 52 MB,